Hello everyone and welcome to Applied Mathematics and Calculus tutorials. In this tutorial we explain how to sketch a function by hand. The problem solved in this video tutorial is very important for students who want to master basic and advanced calculus topics, as well as for students who want to prepare themselves for the Advanced Placement Calculus exam, that is, for the AP Calculus exam. But before I start with explanations, I need to mention that all engineers, physicists, and scientists need to know how to sketch basic functions by hand. This is a fundamental skill that is necessary for engineering profession. Furthermore, by learning how to sketch a function, one can obtain a deep and intuitive understanding of mathematics and behavior of functions. Finally, before I start with explanations, I have to mention that it took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. We will sketch this function by performing several steps. In the first step, we will determine the zeros of this function. Obviously, this is a rational function. The rational function is a ratio of two polynomials. The polynomial in the numerator is 2x and the polynomial in the denominator is x minus 3. The zeros are determined as the zeros of the polynomial in the numerator. Consequently, we have 2x is equal to 0. And x is obviously equal to 0. And that's the 0. Let's sketch this 0 on the graph. Over here, I will sketch our function. Here's my x-axis, and here's my y-axis, and I will use the red color to sketch the function. Here's 0. Perfect. Next, we need to determine the domain of this function. Number 2, domain. Obviously, this function is defined everywhere except at x is equal to 3. Consequently, the domain of this function is x is in the interval from minus infinity up to 3 and not including 3, then union with the following interval, 3 up to plus infinity. Next, we need to determine the monotonicity of this function. That is, we need to determine the intervals for x in which this function increases and intervals of x in which this function decreases. Let's do that. We need to compute the first derivative of y, dy dx. Since this is a rational function, we have x minus 3 squared. And let's see what do we have in the numerator. We have the first derivative of 2x. We have 2 multiplying x minus 3. Then we have a minus sign multiplying 2x. And over here we need to take the derivative of this expression. Obviously the derivative is 1. And as the result, we obviously have 2x minus 2x, that's 0, and we have 2 minus 3, that's minus 6. We have minus 6 over x minus 3 squared. Obviously, this is always negative. That is, our function y is always a decreasing function. Of course, the function is not defined at x is equal to 3, so we omit that point. Perfect. In the fourth step of sketching this function, we need to determine the vertical asymptotes. That is, we need to determine the values of x for which this function goes to plus infinity or to minus infinity. And these values of x should be finite. Obviously, this function is not defined at x is equal to 3. And x is equal to 3 is a good candidate for a vertical asymptote. In fact, x is equal to 3 is a vertical asymptote, and I will show this in 1 second. To show that x is equal to 3 is actually vertical asymptote, we need to evaluate two limits. The first limit is limit when x approaches 3 plus, I will explain this notation in a second, of our function. Here's our function, 2x over x minus 3. So what is this notation 3 plus? Let us first sketch a vertical line over here at 3. We have 1, 2, and 3. Here it is. And let's sketch a vertical line. Here's a vertical line. I will use a dashed line. This limit value means the following. We are approaching this point, the point 3, from the right side. That is, we are approaching it from this side. And we want to see what's happening with this function. If we substitute 3 plus here, that is, if we substitute 3.000001, for example, very small value, we will obtain that 2 times 3.0001, we will obtain something finite over something that's very small and positive. I will denote such a number as 0, but in front of 0 I will add plus. And this is equal to plus infinity. That is what we figured out. We figured out when we approach this function from this side, the function will go up to infinity. That is, it will go like this. Perfect. Now, let's evaluate the second limit. As you might suspect, we need to evaluate this limit. Limit when x approaches 3 minus of our function, 2x over x minus 3. That is, we are approaching this point from the left side, from this side. And we want to see what's happening with this function when we approach the this line from the left side. For example, x can be 0. Actually not 0, we should be careful here, 2.99999, for example. In the numerator of this expression, we obtain a finite number. This is because 2.999 multiplied by 2 is something very close to 6, however smaller than 6. So we have finite. However, in the denominator, we have a very small number, and this number is obviously negative. I will denote the fact that this number is negative by 0, and in front I have a minus sign. And consequently, as the result, we have something finite divided by something very small and negative, and that's minus infinity over here. That is, when we approach this function from this side, our function goes to minus infinity. Perfect. To summarize, we concluded that x is equal to 3 is actually a vertical asymptote. The next step is to determine horizontal asymptotes. To determine the horizontal asymptote, we need to evaluate these limits. First of all, we need to see what happens when x goes to plus infinity. What happens with this function? Let's see. We have 2x over what? Over x minus 3. To evaluate this limit, we will divide the numerator and denominator by x. And as the result, we will obtain 2 in the numerator, and in the denominator, we will actually obtain 1 minus 3 over x. Let's see what happens over here. We will have 2 over 1 minus 3 over infinity. This term will go to 0, and consequently we will have 2. Perfect. Okay, this is a very important conclusion. We concluded that when x goes to plus infinity, this function will approach 2. And over here, again, I will use dashed lines. So here's one dashed line on this side, and we will see what happens on the other side. So what happens? When x goes to plus infinity, the function will go to 2. Will it approach from this side or from this side? Well, we need to conclude. Let's analyze what's happening. We determined that this function is always decreasing. This is a very important observation. And we concluded that it has a vertical asymptote. So somehow it will start from here and it will decrease, 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 and in infinity it will approach 2. It will never reach 2 for finite values. This is very important to keep in mind. However, somewhere in infinity it will approach 2. This is a very important observation that enables us to sketch this branch of the function. And the function, our beautiful function, looks like this over here. Now, let's see the other horizontal asymptote. To determine the other asymptote, we need to evaluate this limit. We need to evaluate the limit when x goes to minus infinity. That is, we want to see what happens with this function when we approach minus infinity. Let's write this limit properly. To evaluate this limit, we will use the same trick. We will divide both numerator and the denominator by x. And as the result, we will exactly obtain this expression. That is 2 over 1 minus 3 over x. And this is obviously equal to 2. We concluded the following. When x goes to minus infinity, our function is actually approaching 2. However, does it approach from the top or from below? That's a very good question. How to conclude? Let's take everything what we determined so far. 0 is over here. Perfect. That's very important observation. Then we concluded that the function is always decreasing. If this is 0, right? Since the function is decreasing, the function needs to go like this. Right? It cannot go up, cannot go down, cannot cross the x-axis over here. It has to go down, and it has to go to minus infinity. This is because minus infinity is actually a vertical asymptote. Now, what happens over here? The function always has to decrease. So if we go from here or from here, the function always has to decrease. Can we cross this asymptote? Well, maybe we can cross this asymptote, maybe we cannot. We cannot conclude that. However, I'm not asking you that in this video tutorial. You can actually determine, can this function actually cross this asymptote by solving 2x over x minus 3 is equal to 2. However, we are not going to go that way. Since the function is decreasing, we can actually conclude that we approach this asymptote like this. And this is our function. It will look like this. Perfect. The function always has to decrease. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.